Hello my friend. Welcome back to You Can Do TV channel. This machine doesn't just crush metal, it devours it. Let's dive into the genius baler by Presse Bull at Delturum's Piacenza depot, where raw scrap meets precision engineering. The process kicks off as scrap cars and vans are dumped into the open chamber, which measures a hefty 6.8 meters long, times 2.45 meters wide, times 2.32 meters high, with an internal bale section of 1.6 meters tall and 0.85 meters wide. Powered by a robust diesel-electric system, its hydraulic oil tank holds 750 L, and the fuel tank stores 100 L. Even the specs sound like they belong to a beast built for battle. Once loaded, the overhead ram descends, crushing scrap into a compact bale. The chamber's enormous pressure flattens steel bodies into dense blocks. A plate ejects the finished bale forward, ready for onward transport. Operators monitor hydraulic pressures and bale density, ensuring consistency. The ground shakes slightly with each stroke, raw power you can almost feel through the lens. Every movement is synchronized, every crush is calculated. It's the sound of chaos being turned into order. Safety barriers and interlock sensors prevent operation until guards are closed. No shortcuts. Completed bales stack neatly, improving handling and transport efficiency. Each bale's uniform dimensions and tight density maximize load value per ton. After loading, the machine is prepped for the next cycle, rapid, relentless, precise. This isn't just scrap processing, it's industrial choreography, massive, mechanical, meticulous. And beyond brute strength, it's engineered for repeatable precision, day after day. Imagine steel in motion. Welcome to ArcelorMittal Hamburg's high-tech steel wire production facility, strategically located at Germany's largest seaport. They process up to 600,000 T of sponge iron per year. The backbone of the process starts with raw materials arriving by rail or ship. Scrap and iron ore pellets are unloaded onto conveyors. Every hour, up to 80 tons of material can be fed into the system, non-stop. In the direct reduction plant, iron pellets are heated to 1,000 degrees Celsius in a reducing gas atmosphere derived from natural gas, extracting oxygen from the ore to produce nearly pure sponge iron. This gas cycle is self-sustaining. Off-gases fuel the system, enhancing energy efficiency. Recycling is central here. Steel scrap makes up nearly half the input mix, giving old metal a second life. Next, sponge iron and steel scrap feed into the electric arc furnace, EAF. Graphite electrodes carry up to 75,000 A, melting the mix into liquid steel. The furnace can reach over 1,600 degrees Celsius in seconds, a firestorm under total control. Continuous sampling occurs inside a robot-manned lab container. Spectrometers analyze composition in real time, while technicians adjust the chemistry to meet exact quality specifications. This live feedback loop ensures every batch meets stringent steel grades used in everything from bridges to engine parts. Molten steel pours into ladles and moves to the continuous casting unit. Glowing billets, up to 16 meters long, 2T each, emerge at 950 to 1,100 degrees Celsius. One billet is long enough to span an entire city bus. They pass through automated rollers and cooling beds, then get cut to length. Each billet is tagged and barcoded for traceability. Throughout this, ISO 9001 certified quality control and real-time analytics ensure uniform mechanical and surface properties. Cameras, sensors, and algorithms work in tandem, catching surface defects invisible to the human eye. Billets are heated and fed into multi-stand rolling mills equipped with 55 to 16 mm pass-throughs. Wire emerges at speeds up to 100 meters per second, then rings are formed, cooled, and conveyed into the stranding line. That's 360 kilometers per hour, faster than a Formula One car, and with far more torque. Bundles up to 1.5 T are tightened with hydraulic presses and wire-bound fourfold, printed with barcoded labels for full traceability. Each bundle could reinforce a small building, compact but powerful. All along, cranes load dense wire coils onto trucks, S-bahn, or ships via a 450 meters quay wall capable of handling vessels up to 70,000 GRT. This logistical edge ensures raw supply comes in and final products ship out effortlessly. The port runs like a circulatory system, steel in, steel out, day and night. From engineering stands alone to precision aftercare, spot-on HSE protocols, CCTV, and automated sensors monitor every step. By integrating mini-mill tech, direct reduction, continuous casting, and high-speed wire drawing, this plant delivers nearly 900,000 T of premium wire annually, while slashing carbon dioxide emissions by about 40% compared to traditional blast furnaces. And they're just getting started. New tech pilots are underway to push emissions even lower. This isn't just steel production, it's industrial symphony. Massive, intelligent, sustainable. It's where megaports meet micro-precision, forging the backbone of tomorrow's infrastructure. Watch raw strength take shape. At United Steel Company in Ghana, the journey begins with wire rods transformed into high-tensile iron rods, grade 4,449, built to British standards. Square pipes are shaped, then galvanized for corrosion resistance. Double helical gears are precision milled on TOS Kurum machines, every curve aligned with purpose. Automated rollers guide each section with millimeter precision, reducing human error and boosting output. Each process is tuned for quality and endurance. It's not just metal, it's trust forged in steel. Look at how coil springs are born. This is not your average assembly line. Pull. It all starts with high-grade steel wire, each cut to an exact length depending on the spring's design. These lengths are then fed into a walking beam furnace, where they're uniformly heated to 900 degrees Celsius using natural gas, a clean and precise energy source. After heating, the red-hot bars move to a CNC coil winding machine. This hot winding method ensures tight dimensional control. Once coiled, the springs head straight to an oil bath for quenching, locking in structural integrity. Next stop, tempering. The coils pass through a gas-fired furnace to restore elasticity and eliminate weak zones. This part of the process is slow because consistency matters, from surface to core. If it's not tempered right, the spring won't bounce back, and in this business, that's failure. If required, the coils go through an automated grinding process to create flat ends. Then it's off to shot peening, where steel beads blast the surface, removing microflaws and relieving stress. That sound? It's durability being forged. Each spring is tested twice, first for scragging, then for loaded ride height. Failures? They don't make it. Only springs that meet all specs move forward. It's brutal, but that's the price of performance. Aerator. Then comes powder coating. A magnetic process attracts paint powder to every surface. The coated coils are cured in an oven at 220 degrees Celsius for 25 minutes, then cooled and boxed. From SUVs to caravans, each spring is built to last. Now that's what you call coil confidence. Discover how a classic bicycle is crafted from scratch. No assembly line shortcuts here. This is a labor of precision, skill, and time-honored techniques. This isn't just manufacturing. It's mechanical artistry in motion. The journey starts with a DXF file, which contains the digital blueprint for every component. Using this data, the team builds a custom die matrix to guide each bend and cut. Everything begins with data, but ends with the hands of a skilled craftsman. The first tool in action? A manual shear, or sisala, used to cut metal sheets down to size. Next comes frame preparation. Steel tubes are carefully measured using a vernier caliper, also called PD ray, to ensure perfect dimensions. Then, each tube is shaped with a bending machine and smoothed using a bench grinder, esmeril, removing rough edges for a clean fit. Here, a single miscalculation could throw off the entire frame. Precision isn't optional, it's essential. It's not about how fast it's made, but how well it endures. Frame assembly isn't rushed. Components are mounted onto a custom-built jig that holds everything in position. Welding follows, with MIG technology ensuring strong, reliable joints. Every weld speaks of experience. And yes, watching those sparks fly never gets old. Then it's on to the smaller but equally vital details. Support brackets, fender mounts, and dropout plates are drilled and installed by hand. Every hole, every alignment, it's all done manually, and it shows in the craftsmanship. It's these details that separate a factory bike from a timeless classic. Once the frame is complete, finishing takes center stage. A motor tool is used for fine grinding and surface touch-ups. The result? Clean welds and a smooth, flawless finish ready for paint or powder coat. Even before the paint, the frame already shines with pride and skill. What stands out most in this workshop is the balance between old-school techniques and modern precision. The use of a Sinfin Electrica, an electric worm drive assembly system, adds force without sacrificing control, especially during alignment and tightening. It's a dance between tradition and technology, and they've nailed the rhythm. In a world full of mass production, this level of care is rare, but here, every step tells a story. And every classic bike that leaves this space is truly one of a kind. Step into the fire and steel. This is where 16-inch steel pipes with 12.7 millimeters walls are born. First, plates are delivered and stacked in the yard. Each plate is numbered and tracked before entering the line by vacuum crane, precision from the very start. Each movement is choreographed, minimizing idle time and maximizing throughput. Before cutting, the material certificate is verified against order specs, no room for guesswork. Edge milling machines remove burrs and ensure perfectly smooth edges. The plate then moves to a 3-roll bending machine, curving with controlled pressure. Post-bend corrections fine-tune the roundness and alignment. Technicians continuously monitor bending parameters to avoid springback or flat spots. Next comes tack welding. Short welds hold the seam before the real work begins. The pipe enters the internal welding MC. High-speed torch action seals the seam from within. Then it passes through external welding MC, building full penetration beads on the outside. Laser alignment systems guide the torch path to ensure weld accuracy across the entire length. Operators are stationed along the welding cells to intervene instantly if the arc deviates. These welds must pass strict, non-destructive tests, with zero tolerance for porosity. Welding wire feed speed and arc voltage are tightly regulated by automated systems. Thermal cameras scan the weld area in real time, flagging any uneven heat distribution. Weld bead shape and size are stored digitally for every pipe as part of the quality record. Every pipe is visually inspected by technicians. Pre-washing removes scale and slag before the pipe expands to exact diameter tolerances. A second wash ensures cleanliness for testing. Washing fluids are filtered and recirculated through a closed-loop system to minimize waste. Each washing station logs flow rate and pH level to maintain chemical balance. Even slight debris can affect the test results. Cleanliness here is critical. Some facilities use magnetized rinsing to remove metallic particles before expansion. Now comes the moment of truth. Each pipe undergoes hydrostatic testing, pressurized beyond its design rating to reveal potential leaks. Ultrasonic weld detection scans for internal flaws, while an X-ray machine provides real-time imaging. Engineers read every pixel. Safety first. Test pressures often exceed 500 bars, simulating extreme operating conditions. Real-time graphs track deformation levels and seal integrity. End beveling machines cut precise angles for future fitting. Finally, a rigorous inspection checks dimensions, weld quality, and surface finish. Rejected pipes are flagged and sent for rework. Approved products are marked, cataloged, and moved to storage, ready for shipping. Digital traceability ensures each pipe can be tracked back to its source plate. Pipes bound for offshore use undergo an additional salt spray corrosion test. Watching this line, you feel the rhythm, plate to pipe, raw to refined, section by section, quality by quality. Beneath this press, steel isn't cut or carved. It's crushed into power, molded in seconds under 1,600 tons of force. Watch closely as a glowing hot billet is brought forward. It's been heated to forging temperature, often over 1,200 degrees Celsius, making the metal plastic and formable. The massive press descends with measured force, squeezing the billet into its new shape with 1,600 tons of pressure. This isn't just brute force, it's controlled deformation. The dies used here are pre-shaped molds. Guiding the material to flow precisely where needed. With each strike, the internal grain structure of the metal aligns, increasing toughness and fatigue resistance. Operators monitor the process in real time, checking alignment and stroke timing. Every movement of the press is logged and controlled via a central system, ensuring repeatability and safety. Once forged, the parts are quickly removed and cooled in controlled environments to prevent warping or cracking. The result? Components strong enough to handle extreme loads, used in automotive, aerospace, or heavy equipment industries. Standing next to a 1,600-ton press, you can feel the ground shudder. It's not just noise, it's power taking shape. When strength meets exact fit, you get fasteners built for extremes. The production of industrial-grade bolts and nuts at this Hagen-Haspy facility starts with raw steel bars stored on-site. Each bar is cut to size and heated, then transferred to forging presses that shape the metal under extreme pressure. After forging, the blanks are sent through machines that roll or mill the threads, depending on the specification. Some pieces are heat-treated in high-temperature furnaces to increase strength and wear resistance. CNC machines are used for finishing operations, ensuring dimensional accuracy. Selected parts undergo shot blasting to clean surfaces, while others are chemically treated for corrosion resistance. For each batch, technicians inspect samples under measuring devices like profile projectors and micrometers, logging data into a quality control system. Completed components are stored by type and lot number in a parts warehouse, ready for dispatch to sectors such as energy, shipbuilding, pipeline construction, or mining. Watching each bolt take shape from raw steel to finished piece highlights the quiet complexity behind industrial assembly, every stage engineered with tight coordination and control. Before an axle supports a train, it survives the fire and force of industrial forging. At this forging line, the axle begins its journey as a steel bar, precisely cut to length. These bars are then preheated in a high-temperature furnace until glowing red-hot, ready for transformation. Next comes the alignment step, where each piece is positioned to ensure symmetry before entering the forging press. Under immense force, the steel is shaped into an axle form, its muscle and heat working in perfect sync. After forging, heat treatment hardens and stabilizes the internal structure, improving durability. A double saw trims both ends to length. Computerized controls ensure each heating cycle is consistent, minimizing thermal stress and maximizing performance. Then it's testing time. An impact test confirms structural toughness, while spectrograph and microscope analyses dive deep into the material's chemistry and grain structure. Each axle must meet rigorous standards. A centering machine prepares the piece for machining. Rough cutting removes surface irregularities and defines basic geometry. Each stage is tracked digitally, creating a full production history for quality assurance. Once inspected, each forged axle is logged and stored for further finishing. Every axle forged here isn't just metal, it's trust, tested and built to endure the long haul. Here's where force meets form. In upset forging, metal bars are first cut to length, then heated until glowing red. The red-hot ends are clamped and pressed with immense pressure, forcing the material to bulge and reshape. This technique increases cross-section without losing material. It's essential for bolts, shafts, and other load-bearing parts. Sparks fly, dies slam shut, and raw strength becomes refined structure. One wrong move, and the entire piece is wasted. That's why timing and alignment are everything here. From a raw steel ingot to a high-performance rolled ring. At GEMEC, production begins with carefully selected steel grades. Mobile spectrometers check raw material compositions on arrival, screening for unwanted elements like sulfur, hydrogen, and oxygen. Ingot cutting is tightly controlled via CAD models to avoid contamination from risers or gates. Each billet is marked to prevent mix-ups, then heated with multi-point temperature sensors, ensuring even thermal distribution. Forging ratios and temperature windows are precisely managed, forming ideal blanks for ring rolling. Using CNC ring rolling machines, raw shapes are compressed and expanded simultaneously, forming seamless rings up to 9.5 meters wide and 30 T in weight. Computer-aided rolling guarantees dimensional accuracy down to the millimeter. In-house heat treatment systems perform quenching, tempering, annealing, and more, adapting properties to the intended use. Over 80 CNC lathes then handle raceway machining, hole drilling, and gear teeth shaping. Every ring is put through a gauntlet of inspections, ultrasonic, magnetic, mechanical, metallographic, to ensure structural integrity. Whether it ends up in a wind turbine or a deep-sea gearbox, each ring carries the silent strength of a perfectly controlled process. Watch as raw steel transforms into a massive double helical gear. Massive teeth take shape on a horizontal boring mill as coolant sprays and cutting tools glide through solid steel. When the sun sets, these poles stand ready to light the way. Let's go inside Tsukuyo's streetlight pole production process, where every weld, every cut, every bend serves a purpose. It all begins with steel sheets, stacked and checked for uniformity. Each sheet is unrolled and measured precisely before entering the cutting stage. Laser or plasma cutters slice long panels into exact sizes, minimizing waste while ensuring consistency. Next comes bending. Hydraulic presses shape the cut plates into tapered poles, each angle controlled down to the millimeter. Even the slightest misalignment here can throw off the final installation. Precision matters. Then comes seam welding. Automated welding machines run long seams from end to end, forming the backbone of the pole. Welds are strong, smooth, and clean, critical for outdoor durability. Welding parameters like speed, current, and arc voltage are calibrated automatically to match the steel grade and thickness. Each adjustment is logged for traceability. Now the base plate is prepared. Thick steel sheets are cut into circular or square shapes, then drilled for anchor bolt holes. These plates are welded to the bottom of the pole with high-strength fillet welds, ensuring firm support once installed. Workers verify the flatness and perpendicularity of the base using precision jigs. Without this, poles could tilt during mounting. Before brackets can be attached, mounting holes must be drilled precisely along the pole body. Each hole matches the design blueprint for component placement, too wide or too off-center, and structural integrity could be compromised. Brackets are then fabricated separately and aligned by hand before welding or bolting onto the pole. At this stage, some designs require extra stiffeners or gussets to support heavier solar assemblies. These are cut to shape and fitted before final welding. After welding, poles are ground to remove residue and imperfections, then pass through ultrasonic tests or visual inspection to ensure structural integrity. Some are even X-rayed for hidden flaws. Poles are coated inside and out to shield them from harsh outdoor elements. This layer acts as armor, helping them withstand years of sun, rain, and wind. Then it's coated with weather-resistant paint. The color isn't just for looks, it adds another layer of protection against UV rays and moisture. Each finished pole undergoes a final inspection. The poles are then cleaned, wrapped, and prepared for shipment across roads, towns, and borders. When the lights switch on, you're seeing a product forged by process, tested by machines, and perfected by hands. In this video, a 47 kg per meter steel rail is being severed using an oxy-propane cutting torch. The setup runs on oxygen at 350 kilopascals and propane at 100 kilopascals, delivering a clean, intense flame that makes short work of hardened steel. Before cutting begins, operators align the torch along the marked cutting zone. The process starts with preheating. The flame brings the steel to its ignition temperature. Once the surface glows red hot, a blast of pure oxygen initiates the exothermic reaction. oxidizing the metal rapidly. Molten iron oxide is blown away by the same oxygen stream, leaving behind a clean kerf. You can hear the hiss and roar as chemistry turns into force. Sparks shoot like a fireworks show from beneath the rail, while the cut slices cleanly through the dense profile. The technique is fast, efficient, and incredibly reliable, widely used in rail yards and steel fabrication. No grinders, no friction, just heat, gas, and precision. It's not brute strength. It's controlled combustion at work. Watch how raw steel bends to will under 160 tons of pressure. This isn't brute force. It's controlled hydraulic power at work. The workshop press begins with simple setup. The operator positions the tube clamp blank on the lower die. Then, with a steady pull of the lever, the ram descends slowly but surely, forming the metal into a clean, uniform bend. Tube clamps like these need consistent angles to fit tightly without stress fractures. That's why alignment and die choice matter so much. And look at that. Smooth, accurate, repeatable. The press resets, ready for the next part. From small shops to big runs, this process delivers power, precision, and predictability. This is the Takisawa TCN 2100, a slant bed CNC lathe that doesn't just cut metal, it commands it. Right off the bat, the model shows major upgrades from its predecessor. The spindle motor delivers 11/9 of a kilowatt, boosting output and torque by 20%. That means faster cuts, deeper passes, and more efficient cycles. You can feel the confidence in every move. The X-axis rapid traverse hits 24 meters per minute. Another 20% leap in speed. For mass production or quick turnarounds, every second saved counts. One of the machine's hidden strengths? Its box-type slideways. Developed through Takisawa's traditional engineering, this setup offers superior rigidity and long-term durability, ideal for heavy-duty metal cutting. Even though it's compact, the working range is impressively wide. Operators get ample space to set tools, load workpieces, and maintain visibility during operation. From roughing to finishing, this lathe handles tough materials like a pro. The machining footage says it all. Steady feeds, clean chips, and no chatter. This machine isn't just a tool, it's a statement of precision and power, designed for shops that demand more from every cycle. This is where gears come alive. Cut not just with force, but with finesse. The workpiece is locked in place, and Ingersoll's cutting tool starts shaping each tooth. Step by step, the profile forms, sharp, clean, and precise. The tool retracts, rotates, then returns for the next pass. No guesswork, no wasted motion. Precision like this doesn't happen by chance. It's the result of engineering discipline. Gear making isn't just machining, it's mechanical storytelling in steel. Welcome to the world of modern metal shaping, where raw aluminum meets digital precision. This is the Samsung SL25 ASY CNC lathe, and it's more than just a turning center. It's a multi-axis powerhouse with live tooling, ready to machine parts in a single setup. The job begins with a 2-1/2 inch 6061 aluminum bar stock loaded into the spindle. The machine spins up, and the turning cycle starts, slicing away outer layers with high-speed inserts to bring the part into rough shape. Next, we cut a stub Acme thread. Known for its flat crests and strong roots, this profile is ideal for power transmission. The lathe executes each pass with micrometric accuracy. No chatter, no compromise. The cutting tool retracts between each pass, allowing coolant to flush away chips and prevent built-up edge. Real-time monitoring ensures that cutting forces remain within optimal limits. Even thermal expansion is factored into the compensation algorithms. This helps maintain dimensional stability during extended runs. Maha. Now it gets more interesting. The y-axis comes into play. Unlike traditional lathes, this machine moves off-center, enabling milling directly on the turned part. A cam groove is cut into the side of the part using live tooling, a rotating cutting tool mounted on the turret itself. The turret rotates swiftly between tools, wasting no time between operations. Every axis motion is pre-programmed, and even complex geometries are executed with ease. Toolpaths are simulated beforehand to detect collisions and optimize efficiency. That's how you get flawless transitions under pressure. Once the groove is established, the machine traces it again to add a chamfer, cleaning up the edge and improving fit and finish. Chamfers also reduce stress concentrations. Small detail, big impact. Multiple offsets are stored in the system, allowing automatic tool compensation when wear is detected. You don't stop production, you stay ahead of it. The combination of turning, milling, and grooving, without moving the part to another machine, means fewer errors and tighter tolerances. Reduced handling also lowers the risk of contamination or damage. After all features are complete, the part is cut off cleanly from the bar. The subspindle catches the workpiece and retracts, preparing for a second operation if needed. This transfer process is seamless and fully automated. Tool holders are checked automatically for runout, and any abnormal vibration is flagged by the control system. Precision here isn't just a goal, it's a guarantee. Watching this feels like watching choreography. Metal, motion, and logic all in sync. Every feature is intentional. Every tool change is rehearsed. Every pass is calculated. From aerospace to automation, parts like these need to be perfect, and machines like this make that possible. This isn't your average chess rook. It's born from solid metal with the help of cutting-edge CNC technology. On the Morisaki NL2500SY700, a 2.5-inch diameter 6061 T6 aluminum bar is transformed with pinpoint accuracy. The bar stock is secured in a 10-inch 3-jaw chuck with a 3.1-inch bore. As the spindle revs up to 4,000 RPM, the dry cutting phase begins at 450 surface feet per minute. The turret tool makes its initial roughing passes, shaving off bulk material to reveal the rook's basic profile. The machine hums with controlled aggression, turning solid stock into sculpted symmetry. Tiny curls of aluminum fly off like metallic confetti, a beautiful side effect of raw precision. Watching this transformation is like witnessing metal take on a new identity. Thanks to its Y-axis and C-axis capabilities, the CNC lathe performs complex movements, crafting delicate flutes and the classic crenellations of a chess rook. Every pass is synchronized. This isn't just machining, it's performance art. What's fascinating is how modern manufacturing can turn a simple idea, like a chess piece, into a precise, elegant object with automated consistency. And when that final shape emerges, carved entirely by machine, it's both a nod to tradition and a showcase of today's engineering muscle. Next, the machine switches to wet cutting at 850 SFM. Coolant flows over the aluminum as the live tooling kicks in. Operators closely monitor the process, adjusting tool offsets and feeds as needed to maintain tight tolerances. The finish pass leaves a smooth, reflective surface that's game-ready straight from the spindle. Step inside a machine shop, where time, tolerance, and technology converge. This isn't just metalworking. It's a symphony of speed, heat, and precision. At the heart of it all, the CTX Beta 1254A, a 4-axis turning center engineered to do it all without missing a beat. The process kicks off with bar stock loaded automatically into the machine. The main spindle rotates the workpiece at high speed, while a turret, equipped with multiple tools, moves into action. From roughing to finishing, the tools carve out every feature with tight tolerances, and here's the twist. This machine doesn't just cut from one side. Thanks to a second spindle and Y-axis movement, it handles both sides of the part without interruption. No need to reclamp or reposition. It's seamless, efficient, and incredibly accurate. Watch closely as the synchronized counterspindle takes over mid-process. The part is transferred automatically, without stopping the cycle. This handoff is like choreography in motion, keeping every detail in perfect alignment. Live tooling adds even more flexibility. Milling, drilling, and even tapping operations are done right on the lathe, turning raw metal into finished components, all without leaving the machine. Coolant flows constantly, preventing overheating and flushing away chips. Every movement is controlled by high-precision linear guides, reducing vibration and increasing tool life. This isn't just turning, it's multitasking on another level. In industries like aerospace and automotive, where tolerances are measured in microns, setups like this aren't optional, they're essential. From start to finish, the CTX Beta 1254A proves what modern manufacturing can do: compress time, increase consistency, and deliver complexity without compromise. Blink and you'll miss it. This is the AF2D6 Ultra, one of the fastest CNC wire benders in the world. Operating with blazing speed and incredible precision, it handles complex 2D shapes with ease. The machine feeds wire automatically, straightens it, then bends each segment with servo-controlled arms, all in one seamless flow. You can actually hear the rhythm of efficiency in every move. There's no manual adjustment here, just raw speed, driven by exact programming. Watching it work is strangely hypnotic. In high-volume manufacturing, this kind of automation isn't just impressive, it's essential. Steel this tough doesn't go down without a fight. What you're seeing is the Everising E530, slicing through a massive SKD61 tool steel bar, 404 millimeters in diameter. The high-torque bandsaw runs with hydraulic feed control, maintaining consistent pressure even as the blade bites deeper. This isn't just brute force, it's smart force. Coolant floods the cut zone, carrying away heat and metal chips, reducing friction and prolonging blade life. Even at full load, the blade maintains straightness, minimizing deflection across the cut. Look at that clean surface finish. That's not just a cut, it's a statement.